So, hello, welcome to everybody. This is the second seminar of the autumn series of the Spotlight Seminar on AI, organized by the Italian Association for Artificial Intelligence. Well, today it's really a great pleasure for us to have as a distinguished speaker Francesca Rossi. So I would like, first of all, to thank very much Francesca for being here, for having accepted our invitation. All of us know very well Francesca. I just want to tell a few words and summarizing the lot of activities she currently do. So Francesca today is an IBM fellow at the IBM AI Ethics Global Leader. She is based in the Watson IBM Research Lab in New York, USA, where she leads AI research projects. A research interest focus on artificial intelligence with special focus on constraint reasoning, preferences, multi-agent systems, computational social choice, neurosymbolic AI, cognitive architectures, and value alignment. She co-chairs the IBM AI Ethics Board, and she participates in many global multi-stakeholder initiatives on AI ethics, such as the Partnership on AI, the World Economic Forum, the United Nations ITU AI for Good Summit, and the Global Partnership on AI. Importantly, she is a fellow of both the AAAI and of EURAI, and she has been president of EJCAI and editor-in-chief of the Journal of AI Research. Currently, she is the president of the Association for Advancement of Artificial Intelligence. So it's really a great pleasure for us to have Francesca here. And Francesca is going to talk about a very interesting topic and very fascinating topic about thinking fast and slow in AI. So welcome, Francesca, to our Spotlight seminars, and thank you very much again.
Thank you, Gianluigi, and the whole Italian AI Association for inviting me. It's really a pleasure to be here and being able to talk about this topic of my recent research projects. So what I will focus on today in this talk is to describe this recent project about thinking fast and slow in AI, which is, as the name says, is a way to be inspired by cognitive architecture, make decisions in order to advance AI, and not just advance AI in terms of autonomous machines, but also in terms of helping human beings make better decisions. So during this talk, I will introduce very briefly the thinking fast and slow theory of human decision making, and then I will show you briefly and describe how our team has decided to translate this cognitive theory into a computational architecture. We call it the SOFI architecture for slow and fast AI. And then I will give you, the main idea of the architecture, which is a multi-agent architecture. So I will describe what the agents are and what the role is. And then I will show you two specific instances of these architectures for two decision-making scenarios. And finally, I will just give you an idea of how we can use the same architecture, not just for autonomous decision-making, but also for human decision support. So first of all, let's think about what is the problem here that we are trying to solve. So what is still missing in AI? AI, especially in the last months and even weeks, has shown remarkable advances in many respects. But is still missing generalizability, the ability to adapt to new scenarios, context awareness and understanding, semantic understanding, and we all know, from even large language models that are so amazing in what they can do, how they can say it, the fluency of their text that they generate, but still they are really lacking in semantic understanding of that text, as well as common sense reasoning and continual learning. So there are still things that are missing in AI, and that the advances that we have seen, that, as I said, they are really remarkable, they still show that these capabilities are missing. So this is the problem that in AI many people are trying to solve. And so there are many recipes for solving the problem, or partially solving the problem. And here I'm just want to direct the attention to a possibility, an option to address this problem that has to do with mixing different techniques within AI, so the so-called Neurosymbolic AI, which may mean many different things, and I will tell you what it means for us in our project. So here I just very briefly outline that AI, as you know, had different phases in the past. AI research, a first phase was mainly to mimic and to model the high-level cognitive capabilities of human beings, so logic and reasoning, planning, search, optimization, and so on, and which was good in terms of mimicking these capabilities, but less good in terms of being able to go out in the real world and take data from the real world, transform it into knowledge, and then apply these cognitive capabilities to knowledge. So it was mostly developed for very controlled decision environments. The second AI phase, in which we are all still in some sense, is the data-driven approaches. So taking data from real life and transforming them into knowledge, and then doing predictions, doing classifications, doing decisions out of that data. And of course, these are the positive a positive view that many perception capabilities can be implemented in that way successfully. So that means that the machine can be deployed in the real world, and with this perception capability can be more aware of what happens around the machine and then make decisions based on that. The current phase, in some sense, is some bodies called reunification. So we want to take the best out of these high-level cognitive capabilities and the data-driven approaches in order to combine them and then possibly to resolve these things that are missing still in AI. One way that one can do that is to still think that humans, after all, are able to do that. Humans are able to learn from data and are also able to develop and use logic-based reasoning capabilities, search, optimization at a very high level. So the idea is to be inspired by what human put in place in order to have the capability to generalize, abstract, adapt, and so on, in order to translate them in some way into a machine and possibly see the same emerging behaviors. So the inspiration can come from the human mind or the human brain. So it can come from cognitive theories or also from neuroscience. In this project, we are being inspired by the human mind, so by cognitive theories of how humans make decisions, and not really from the neuroscience that tell us how the brain is structured and what the functions of these different pieces of the brain are and how they connect with each other. We hope that this can be successful, whether you're inspired by neuroscience or cognitive science, also look at how humans do this, because we have a more mature AI technology compared to what was inspiration and the deployment done in the beginning of AI, and also a better knowledge of how both the mind and the brain works. So in particular, here in this project, we are inspired by the thinking fast and slow theory of how humans make decisions, also called thinking fast as system 1 and thinking slow as system 2. So this theory is very simple to state. So it says that basically we have two main broad modalities in which we make decisions. One, thinking fast, system 1, that is very fast, almost unconscious, automatic, and we use it when decisions are very easy to make or we are very familiar with the problem to be solved. We use it kind of 90% of the time, and sometimes can have some Thank you. As well as thinking slow, or also called system 2, which instead is much slower, usually conscious. It requires all our effort, and we use it for complex decisions. The system one, as I said, is very parallel and local, so it can perform very cognitively easy tasks. And system two instead really is global because it requires all our attention. So sequential, meaning that we cannot use system two for two different problems in parallel. So sometimes the two things are combined. System two search is sometimes supported by system one kind of heuristics. And in many problems, not all, but in many problems, we start by using system two in solving the problem when the problem is still not familiar. And then we move, when the problem becomes familiar and we have enough experience, we move to using system one. And this, I'm saying this because this is an emergent behavior that we will see also in our architecture. Okay, so how did we decide to translate this very general theory into a cognitive architecture? This is a multi-agent architecture where we put together several pieces, agents, that take overall a problem instance, and at the end they generate a decision, so a solution for that problem. You can see here that there are some fast, so-called fast solvers, which doesn't mean fast computationally, but just to remind us that they are similar to the thinking fast approach. And these fast solvers are solvers that can solve the problem without reasoning about the problem, but just relying on past experience on solving that or similar problems. Then we also see some slow solvers. Again, slow doesn't mean necessarily slower computationally, but it just means kind of thinking slow attitude. And these slow solvers instead solve problems reasoning about the problem, doing logical reasoning, symbolic reasoning about the problem. So they don't rely just on experience, but they reason of the problem instance that comes in. Okay, so we have fast solvers, slow solvers, and then we have a metacognitive agent that decides which solver is going to make the decision or solve the particular problem instance. And both the fast solvers, the metacognitive agent, the slow solvers rely on some models of the world, decision environment, models of others, if we are in the decision environment where other agents, other machines or human beings are involved, and model of self, which just means a way to record all the activities that this machine has done. So who made the decision, whether it was a fast solver, a slow solver, what the metacognitive agent decided, what the reward for this decision was. So all the things that were done in the past by this machine. So let's go a little bit more about these solvers. So as I said, there are system one or fast solvers and system two or slow solvers. As I said, system one just rely on past experience. System two reason about the problem. So then we have the metacognitive agent. So here, the metacognitive agent does not solve any problem instance that comes in, but it just decides which solver is going to be solving that problem instance. And in particular, you may see in the picture already that the fast and the slow solvers are not symmetrically, is not connected to the metacognitive agent in the same way. So the fast solvers start solving the problem before the metacognitive agent starts thinking about who is going to solve it. So the fast solvers are activated immediately as the problem instance comes in and generate a solution for that problem. At that point, with that solution and the confidence level, this is given to the metacognitive agent, and this is the input to the metacognitive agent, the problem instance and the proposed solution from the fast solver. At that point, the metacognitive agent decides, should I accept the solution that is provided to me by the fast solver, or should I activate a slow solver instead because I don't trust enough the fast solver, or I don't like this solution, or whatever reason? So the metacognitive agent has this problem to solve, either to accept the proposed solution from the fast solver or to activate a slow solver. And then if they activate the slow solver, then it is the slow solver that will make the decision or solve the problem. So There are some various design choices that we made in designing this architecture. First of all, we decided to have a centralized metacognitive agent. This is not true in general for any cognitive architecture. There are some cognitive architectures that have a very decentralized metacognition. So here we decided to have an agent that performs the metacognition, meaning the reflection about who can solve the problem, what has been done in the past, and then making the decision whether to accept the fast solver solution or to activate the system 2 solvers. Also, another design choice that I already mentioned is that this is a system 1 by default architecture, meaning that system 1 is activated, the fast solver, as soon as the problem comes in. It doesn't wait for the metacognitive agent to decide to activate it. And this is similar to what happens in a human being, where our system 1 is very reactive and unconscious. We don't think about activating it explicitly. So we decided to use the same kind of modality where system 1 is activated by default as soon as the problem instant comes in, and then later on, maybe the system 2 solver is activated if the metacognition decides to do so. And this is to minimize the time to action when there is no need for a system 1 solver. Another thing is that we are not making any assumption that the fast solvers are faster than the slow solvers in terms of computation time. So it may be that case, but not necessarily. So in some sense, this is a neurosymbolic AI architecture where because most of the time it could be that the fast solvers are using a data-driven approach that like a reinforcement learning approach that looks at the past experience and decides what to do next. And the slow solvers could use a symbolic logic-based approach. So in some sense, the architecture is the metacognition of the architecture is being an arbiter deciding whether to use a neuro or a symbolic AI approach. So this approach to neurosymbolic AI is based on the architecture, on the multi-agent architecture, and does not mix the neuro and symbolic. Maybe some solvers can be a mix of the two, but mostly, it keeps the things separate and then uses metacognition to decide which one to use. So there are many other ways, of course, of achieving neurosymbolic AI. Some are completely different on a full integration, like logic neural nets or tensor neural nets, full integration of the neural and symbolic approach. Other ones, they combine neuro and symbolic components in a pipeline or in parallel or sequentially, so on, but ad hoc for each specific task. So in some sense, they also use a little bit of neuro and a little bit of symbolic separately, but it's the human being that, knowing the task that has to be solved, in some sense provides the metacognitive capabilities. SOFI would like to use kind of the second approach, but with the metacognition inside the machine that autonomously decides who is the best solvers to solve a problem. So let's look at two instances of this architecture. The first one is for sequential decision making on a constraint grid. So we are moving in a grid. This is the picture of a grid where we have an initial cell, a goal cell, and then the machine has to build a trajectory from the initial to the goal cell, trying to avoid the constraints. The constraints in the grid are on specific cells that if you go there, you get a penalty, or on specific moves. Every cell has up to eight possible moves in all the possible direction, and there can be penalties associated to each one of these moves. So this is the goal, to build trajectories trying to minimize the penalty that you get. So in this case, we use an instance of SOFI where we use reinforcement learning as a fast solver, and then we use MDFT, which is a specific theory that is shown to be mimicking human decision making, as a slow solver. So it's a logic reasoning solver, which, however, accounts for some of the irrationalities of human decision making. Okay, so here we decided to consider this architecture, but actually we consider 5 different versions of a reinforcement learning agent for the fast solver, with 5 different degrees of randomness, because we wanted to see whether the architecture could adapt to different fast solvers with different capabilities. So we did an experimental evaluation to show the behavior of SOPHI, the architecture, with using S1 alone or S2 alone. Or humans alone. So, and then we asked what's the difference, who is performing better in terms of trajectory length, trajectory reward, and time to build the trajectory. So this is a summary of what we saw. So first of all, as I said, we have 5 different versions of the S1 solver. And we saw that SOPHI can adapt to the capabilities of this solver. So the reward level obtained in these trajectories that are generated as SOPHI is very stable, and it does not really depend too much from the fact that the solver is more random or less random in its decisions. So of course, how can it do that? It does that because if it realizes that an S1 solver is very random in its decision, it uses it less and it uses more the S2 solver, which means also that it takes more time, because in this particular instance, not necessarily in general, but in this particular instance, the S2 solver is computationally slower than the S1 solver. Over time, also, SOPHI learns. Over time means one trajectory after the other one, and we accumulate experience. Over time, SOPHI learns to calibrate the use of S1 and S2 to maintain a stable trajectory reward quality. And also, it increases over time the use of system 1. So similar to this emergent behavior that I told you, it happens in human beings. We start with using most of the time as system 2, and then we pass to using system 1. But the last point here is that SOPHI, in terms of all these criteria, the trajectory length, quality, which means reward and penalty, and time to build it, is better than using only the fast solvers or only the slow solvers. So it means that putting them together and combining them through the metacognition allows to be better along this dimension that I mentioned. So here there are some results that, for example, this first one, it just shows that all the versions of SOPHI that we considered, and these are the different colors that define the version of SOPHI, they are better than system 2 alone. Again, trajectory length, reward, and time to build it. Each one of the graphs is about one of the criteria: length, reward, time. And the last one on the bottom right is the JS divergence with human trajectory. So all of them are better than using system 2 alone. Then we go into graphs that on the x-axis, they have the trajectories over time. So from trajectory 1, 2, 3, up to trajectory 500. And over time, we don't start from scratch in the next trajectory, but we keep the experience of the previous trajectory. So we wanted to see how SOPHI learns over time by accumulating experience and using that experience. And here is the graphs, 5 different graphs, because as I told you, we want to see how SOPHI behaves with 5 different versions of the fast solver, which have different degrees of randomness. The more you go to the right in these 5 graphs, the more is the fast solver very deterministic. So the first graph that you see on the left, the fast solver is completely random, and the one that you see on the right, the fast solver is not random at all. Just optimized based on past experience. So here we can see that SOPHI, which is the orange one, on the y-axis we have the trajectory length. SOPHI builds shorter trajectories than S2 because the orange is very, very comparable, but never above the blue one. And also not only is not above the blue one, but is also much more stable over time. It doesn't go up and down like the blue trajectory. The second one is the trajectory reward. So same setting, the 5 different versions of the fast solver. And here in terms of trajectory reward, you see that phi, again the orange one, builds trajectory with higher reward. So it's always on top. Here top means better. So higher reward than using the slow solvers alone. And again, is always more stable. It doesn't have all these variation. So that's the trajectory reward. And the last one here is about time for trajectory. And here again, the orange, which is SOPHI, is always faster in terms of time, which is on the y-axis, than using the S2 solver alone. And the reason why it's faster, because it doesn't use the S2 solver all the time, but it also uses many times the S1 solver. So you see that these trajectory here are built by interleaving moves made by S1, moves made by S2, and so on. So every move, the machine decides whether it should be an S1 or an S2 solver to do it. Here it shows the usage of system 1 or system 2 solvers within SOPHI over the various trajectories. So you see that here the system 1, which is the blue one, and the system 2 is the orange one. So over time, over the 500 trajectories, is used more and more, the system 1, and less we use the system 2. So more moves are being made over time by system 1. Of course, with the different versions of system 1 solver, the 5 different versions, the situation is different, because when the system 1 solver is very random, like the left graph, yes, there is an increase in using system 1, but still much less than using the system 2. Instead, where the system 1 is completely optimized, far right here, then we really use system 1 almost immediately. We switch and we use system 1 almost 100% of the time. Okay, so we also explored the use of SOPHI for another decision scenario, which is symbolic planning, what we normally would use a planner, a state-of-the-art planner, to solve it. So here, we still are in the space of sequential decision making, but while in the grid, SOPHI was called at every move to build a trajectory. So if we had to build a trajectory of length 10, we would call SOPHI 10 times, one for every move. Here instead, we call SOPHI for building the whole plan for a planning problem given in input. Okay, so call it just once. And again, here SOPHI has to decide whether it wants to use a slow planner, which in our case is the state-of-the-art symbolic planner, or whether to accept what the fast planner is going to propose to SOPHI. And the fast planner in this particular instance is either a case-based or a transformer-based plan generator. Okay, so the first experimental setting is using SOPHI for epistemic planning. Here we use a state-of-the-art epistemic planner, EFP 2.0, as a system 2 planner. And then as a system 1 planner, we use a case-based plan selector. So this system 1 planner does not generate new plans. It just picks up from the plans previously generated by EFP 2.0, so the system 2 planner. It picks up the plan that it thinks is the best plan for the new problem that came in. Either because we solved that problem or because we solved a similar problem in the past, it picks up the problem using some notion of distance between plans and planning problems. So here you see that we compare the System 2 Planner, EFP 2.0, with 4 different versions of SOPHI, and one of them using different notion of distance for the case-based planner, but one of them in particular, the one that uses the Jacquard distance, you see that it can solve many more problems, 222 instead of 139, with less time, because of course many times it doesn't use the planner, the real planner, but it picks up a plan from the repository, and with a very high correctness, in average correctness level, because if you just use the EFP planner, you may run out of time, and so many times you have correctness 0 because you don't solve the problem at all. Instead, with combining the fast and the slow planner, you can solve the problems many times correctly, many times not correctly, but not with the degrade too much incorrectness. Okay, so now let's look at the other things we did for classical planning, not epistemic. For classical planning, we said, let's also build a planner which is not just picking up plans from the past experience, but is generating a new plan. So we had this idea of using a large language model to generate plans for classical and epistemic planning problems. So we called it Transformer, just to say it's based on transformers. We took a large language model already fine-tuned for some structured text, in particular for code generation. This is called Code T5. And we further trained it for solving planning problems. So here, and then we tested, before including it in SOFI, we tested it whether it was a good model, so it means whether it can perform well on some test data set by providing the plan that was associated to a certain planning problem instance in the test data set. And then we tested also as a planner, because maybe the as a model is not good, because it doesn't give exactly the plan that is the label for that test item, but it is a good planner because it generates something that is a plan, even if it's not the label in the test data set. So in both cases, the transformer performed very well because compared to other models like Codex, GPT-2, and so on, the transformer was able to perform well on several data sets, and also as a model, and also as a model, as a planner, it performed well in terms of generating a valid plan. Okay, now we have this transformer, and we decided to plug it into the SOFI for planning architecture as a System 1 planner. So here we see the result of these experiments, where we have for classical planning. For now, we have just for classical planning. So the first table, it shows you the solved problems, the time, the correctness, and then how many times it calls the S1 planner, comparing the 4 different versions of SOFI with different versions, the Jacquard distance, Transformer as a System 1 planner, a mix of the two, and the FD here is fast downward, which is a state-of-the-art classic planner. So as you see that some versions of SOFI, either the one with the Transformer or mix, which just means Transformer plus case-based mix together, they can solve many more problems, 671, with, however, on an average, more time if you use Transformer. You see, Transformer takes 18 seconds in average compared to the 12 seconds of FT. Okay, so then we said, okay, correctness is much better, 0.89 instead of 0.84. So correctness is good. We solve many more problems with SOFI, but time is not good. So we went and examined time a little bit better. And here you see a second graph where it shows on the x-axis the complexity of the problem. In particular, here we just considered for these blocks word problems, and with different number of blocks. So the colors here just represent the different number of blocks. So from left to right, you have the pink as 4 blocks, the green as 5 blocks, and then you have 10, 11, 12, and 13. So from left to right, problems are more complex, and you see the time that it takes to solve them. The blue dots are the time taken by SOFI with Transformer, and you see that yes, it increased a little bit, but not very much, and it still remains very low. And instead, the orange dots or X's is the time by fast downward, so the planner, the classical planner, which take very little time if the problem is easy, even less than SOFI with Transformer, but they go to the time limitations for more complex problems with more blocks, while the SOFI with Transformer keeps being very low in time, so it goes lower than the Transformer. So again, solves more problems, it's has better correctness on average, and it is for complex problems, it also takes less time. Okay, so the last topic that I wanted to talk about is the use of SOPHI, not to make autonomous decisions, but to help humans make better decisions. So as a decision support system. And here we would like to embed in SOPHI a nudging framework where we envision 5 different modalities of interacting between the machine and the human being. These are the one on the bottom left. So 2 of them are very obvious, like one where the human does everything by himself, and the other one where the machine does everything by itself, and the other 3 in the middle instead are nudges situations in which the AI nudges the human. So in defining this nudging framework, we exploited the fact that we know that humans are going to make decisions using the thinking fast and slow theory. So we are going to use either a system 1 or a system 2, or even to use metacognition to choose which one to use. So that's why you see here 3 nudging situations: one where the machine nudges the human to use the system 1, one where it nudges to use system 2, and the other one it nudges to use metacognition. So from left to right, you see a progression of more autonomy for the human being, but also more cognitive load. Okay, so on the right-hand side, instead, you see a possible way of implementing these 3 different nudging situations. To nudge a human being to use a system 1, a very simple, naive way of implementing it would be that the machine shows its recommendation for solving a problem to the human being immediately, without letting the human being being able to think about it, and then the human makes the final decision. So that means that the human will have a very strong anchoring bias on what the recommendation given by the machine, and most probably we use the system 1, which is the one that uses biases and in making decision. The second nudge is to use system 2, is basically opposite of this. So the machine does not give immediately the recommendation to the human being, but let the human being have enough time to think about the possible decision, and then the machine communicates the recommendation, and then the human may compare if they are different, and here is stimulated if they are different to use system 2, and then makes the final decision. Instead, using nudges to use metacognition is the same as using system 2, but here the machine does not give the recommendation when after the human being has made the first decision, but actually ask the human being whether it was the recommendation. And this stimulates the human being at the metacognitive level to decide, to think about whether he's confident or not in his initial decision, because if he's not confident, then maybe he wants to see the recommendation of the machine. So again, this is how we plan to embed these 3 different nudging frameworks, nudging situations, into a framework where we decide when to use one or another one of these nudging situation, depending on the confidence level that the machine has in the current solution, and on the past experience of the machine and the human being, whether for those kind of solutions the machine has behaved better or not. And then depending on these 2 axes, so the confidence level and the past performance of the human being versus the machine, we decide to use the nudging towards system 1, system 2, or metacognition. So in some sense, well, I'll leave this. So in some sense, by using SOPHI as a decision support system, so we have 2 ways of exploiting the thinking fast and slow theory. First, because the machine itself is implementing a sort of thinking fast and slow with this fast solver, slow solver, the metacognition, and so on. But also because the machine is supporting the human being by exploiting the knowledge that the human being will make the decision using the thinking fast and slow theory, using these 2 broad modalities. So in some sense, the machine in this nudging framework can actually be implemented by a meta-SOPHI architecture, which has the same pieces, but where the solvers can be humans or simulating humans, or a SOPHI machine itself, and they implement these various nudging situations that we said. So this team, I just want to say a few words about the team that is working on this project with all these dimensions that I mentioned, the various instances, the cognitive architecture, the the metacognition, the decision support system approach, and so on. And this is a very broad team with many people in many universities, as well as IBM, of course. But the point is that it's very multidisciplinary, where people expertise in AI, both in the data-driven approaches and in the symbolic AI approaches, ML, KR, planning, and so on. There are people experts in software engineering, in mathematics, neuroscience, philosophy, and cognitive science. So it has to be a very multidisciplinary team to really be understanding how to translate a cognitive theory into an architecture, an AI architecture. If you want to know more about what the project is doing, the papers we publish, the events we organize, and also to be in contact, reach out to us with questions or anything about the project, we have this website that you can find, and you find all the information about all the different dimensions of the project. So I'll stop here and I welcome any question. Thank you.
So thank you very much, Francesca, for this very, very nice talk. It's the first time I've seen such a complete architecture relating System 1 and System 2. So it's and the findings are also very interesting and in some cases also surprising. So thank you very much. So it was also very inspiring for me. I think there are a number of questions from the audience that can write down on the chat. And I take now the opportunity also to introduce the scientific committee of the Spotlight Seminar initiatives. We have Giuseppe De Giacomo, Marco Marate, and Chiara Maghedini. So I ask them to start posing their questions and their comments to your talk.
Mm-hmm.
Okay, I can start. Okay, Francesca, so just a curiosity. So in the second instance of your architecture, you mentioned classical and epistemic planning, basically. I'm curious to know whether, so if you envision the possibility to have other type of planning, like numerical, mixed integer, continuous discrete planning. So
yeah, these are just instances. We tried. We had people in the team with expertise on those kinds of planning. But definitely, we are open. And in fact, what we plan to do in 2023 is even to open the use of SOFI, because the code is released open source and we will make it more even easier to use. So to open the use of SOFI for others people to experiment with other kinds of decision scenarios, whether within planning, but also in other domains. So we right now the code is there, but maybe we need some work in order to make it easy so that people can plug in whatever they want as a fast solver, a slow solver. And if you want to experiment with different kind of planning, you just need to build, to plug in a state-of-the-art planner as a system 2 planner, and then use one of the fast planners that are there, or plug in your own fast planner. But definitely, yes, we are open, and again, not only we are open to experiment ourselves, but also to let everybody experiment and see how it behaves.
Thank you, Francesca, because I have the feeling that if you move to, let's say, planning languages, as I said, like numerical planning or mixed discrete continuous, so your architecture, your solution could have even more impact.
Okay, well, let's try together. Yeah.
So Francesca, but just also for me a curiosity, do you envisage application behind planning? So which kind of problem can we address with this fast and slow approach?
Yeah, so we started with this in some sense domains, because these are the domains where there are a lot of benchmarks, so we could compare with others, right? But yes, we envision any sort of decision scenario. For example, we we recently just submitted a proposal for a to a funding agency that is interested in very complex decision scenarios under time constraints, where the system 2 planner could have a better quality decision, but sometimes it may be taking too long, and then you need a very capable system 1 planner that, if you have enough experience, can take over when the decision, when there is not enough time to use the other one. So, and those are very realistic and complex decision scenarios with various agents that make decisions, and then they recommend decisions also to a final decision maker. So in that scenario, we will see the use of SOFI both as autonomous decision, but also as proposing decisions. Then the final decision maker will either adopt or not. So yes, we are planning to look at more realistic decision scenarios, but I don't think there is a specific characterization of problems where we think that SOFI could work better or worse. I think that it is applicable to almost any decision scenario.
Thank you, Francesca. So from those that are attending now online, there is a question, first a comment, and then a question by Edlira Hika. Thank you for the talk. The neurosymbolic approach is what seems more efficient now in AI. Could you please add more details about the metacognitive components algorithm? So how this component works?
So the metacognitive component for now is a symbolic AI component. So it's very explicit. It's not based on data, and it's not a neural net, for example. And this metacognitive component has basically two phases. In the first phase, it doesn't even consider the system 2 possible solver, but it just evaluates the quality of what the system 1 solver is proposing to do. So the system 1 solver is proposes to solve to a certain solution to the problem that has to be solved, and it gives a certain confidence. So the metacognitive component in the first phase, it says, am I happy with what the system 1 solver is giving me? Is the confidence high enough? Do I trust the system 1 solver based on past experience? How many times did I use it and it made mistakes? And so on. So first level is like this. And if everything goes well, the system 1 solver solution is adopted without even looking at the system 2 option. If instead something in this first phase is not acceptable, then there is a second phase where the metacognitive component really compares the use of system 1 and system 2 and makes the decision of whether to adopt system 1 or use system 2. And the comparison is made on looking at the expected reward of using the system 1 solution or using the system 2 solver, the difference between this expected reward, and the fact that if I use the system 2 solvers, I will have to pay a cost because the system 2 solver has not done his work yet. So it will take some time to generate the solution, while instead the system 1 solver, no matter whether it was really fast or slow, it has done its job already. So I am in a situation now where I don't need to pay more in terms of time to use the system 1. So these three things are combined in some way: expected reward of the move decided by system 1, expected reward of system 2, and expected time of system 2. And if things are combined in a certain way, then I decide to adopt system 2 if I see that by using system 2, I expect to gain in reward and not paying too much in additional time that I have to spend.
Thank you, Francesca. So another question. Carlo is asking, could we frame the fast solvers as heuristics for the slow solver and the metacognition agent as a heuristic selector? What do you think?
This is a possible way to use the metacognition, but for now, the experiments that we did, the fast solver can completely solve a problem. It's not just for providing heuristic for the slow solver, and the slow solver, which can have heuristics inside, but is completely solving the problem. So these two are two alternative ways to solve the problem. But it doesn't mean that the S2 solver could have heuristics inside. But these heuristics have been defined before plugging the S2 solver into the SOFA architecture. But in the future, we could think about because in some sense the system one solver evolves over time because it learns from experience, and this could then be used at a certain point to plug in updated heuristics into the S2 solvers. But we have not experimented with that yet.
Okay, thank you. Are there other questions?
Yeah, if I can, I have
Chiara, please.
two questions. Well, first of all, thanks for the talk and also for the idea of opening up the system, which I think would be really great for research and for the community. The first one is a curiosity about Transformer, and in particular, how big was the effort to, let's say, transform Code 5 into Transformer? And the second one is more about other applications. I mean, one of the problems, for instance, in interactive AI or in dialogue systems, for instance, is the fact that everything is glued together, and sometimes these very big conversational agents are difficult to trust. So would this metacognition agent could be considered a kind of, I don't know, dialogue manager? So also to distinguish in situation while your let's say platform can respond fast or can interact fast, and the situations in which it really needs to be careful and to interact slow.
Yes. Okay, so the first one is about the building of Transformer starting from Code 5. I think we used about 14,000 size of 14,000 item in the training data set to further train Code 5 for one of the domains that we are experimenting in planning. And we looked at 4 domains: Bloxword, I don't remember the other ones, but the most difficult one was driver log. So various difficulty of domains in classical planning, but each one we used about 14,000. And then we also experimented with some transfer learning. So once you further training for Bloxword, how much more data does it need to train it over for the other domains and so on? But that's the order of magnitude. And the second one, yes. So we envision a notion of trust that is at the metacognitive level. So, because in some sense, when you trust, I think when I trust a person, I don't know all the details of his algorithms to solve all the possible problems, but I trust that he or she will choose the best algorithm for each problem that comes in. So I trust the metacognitive abilities of that person and judgment, the metacognitive judgment of that person. So that's why we envision a notion of trust which is at the metacognitive level, where the metacognitive agent, which doesn't do that right now, but we plan an evolution of the metacognitive agent that also makes decisions based on how trustworthy are the various solvers, and not just how much time they took and whether they made mistakes. Yes, mistakes, yes, but also other trustworthiness. So the metacognition is going to take care of choosing the solvers that are best for the scenario with the best trustworthy and the most appropriate trustworthy approach. And then from the outside, I just have to trust the metacognitive agent. So that's the idea that we have for this higher level trust rather than trusting each single solver.
Thank you.
Francesca. Thank you. So, other questions from the audience over here?
So maybe I have a question. So what kind of formal guarantees you envision in a system like this, right? So for now you have some statistical guarantees, things works, okay, but what kind of property a system like this, formal property a system like this should have, right? So I don't know, the metacognition capability, certain characteristic, maybe the things that you plug in should have certain characteristics to guarantee overall that the system works in a proper way.
Yeah. So we didn't study yet this from the formal point of view, but what we envision is exactly what you said. No, that to characterize some features of these solvers that you plug in, and then to infer characteristics or formal properties of the whole machine given the properties of these solvers. Okay, and the characterization of a specific metacognitive component, because yes, you can plug in various solvers, but you could also modify or change or plug in a different metacognitive component. So our idea is to, with some formal methodologies, to characterize these different pieces, ages, and then based on their characterization, build the compositionality. Say, okay, so then what can we say about the overall machine? So that's planned to do, but we haven't done it yet. For now, we wanted to see just this emerging behavior from the experimental point of view.
Thank you. Thank you. So, are there other questions? We have a lot of questions and discussion, so I think it's time just to thank again Francesca. So it was a really wonderful talk, Francesca. We really enjoyed it. Oh yes, there is just another one. I want to miss any question. So Gerardo Seminary, do you think that properties related to computational cost can also be incorporated? Thank you, Gerardo.
Yes, I think so. Yes, I think that definitely, the characterization of the solvers, for example, may include characterization of their computational cost, which may transfer, be inferred at the level of the whole machine, given the computational cost characterization of the solvers, and of the metacognition. So it's just one other dimension of possible characterization of the solvers and the metacognition. But in general, I mean, I really agree with Giuseppe that there is this idea of inferring formal properties of the machine from formal characterizations of the different agents.
Yeah, this can be a very interesting avenue for research. We are all inspired by these ideas, all those that we like formal characterization and formal methods. So I think this would be really some very interesting to study and explore. So Francesca, thank you very much. We really appreciate that you spent this afternoon with us. So it was really a great pleasure for me as a president of the Italian Association to have you as our distinguished speaker here today. And thank you the committee for being here. And just want to tell you that the seminar will be posted on our YouTube channel so that you can see it again and divulgate among your colleagues. And we will see in January for the third seminar of this period. So thank you again and bye.
Thank you. Bye-bye.
Bye.